Hi, this is Dylan Murphy from Ocient. I'm the Director of Product Management. And today we're going to talk about leveraging the power of geospatial analytics at Hyperscale. And we're going to do that by using some examples from the automotive industry. So in this demo, we're going to be looking at some challenges that the automotive industry faces. And when you look at where the automotive industry is headed and what they're trying to do, all of it sort of relies on very large scale hyperscale data behind the scenes. So as they look to get more into deeper level of autonomous driving and autonomous vehicle fleets, there's data related to sensor data, map maintenance, connected car data that all becomes important in driving the autonomous vehicle initiative. And as they continue to fight for the electric vehicle space and sell more electric vehicles, they need to understand charging, their charging networks, infrastructure planning, battery optimization, and the charging experience. All of that relies on a tremendous amount of data related to the network and battery performance. And then when you look at delivery and logistics, which is another big part of the automobile company's strategies, looking at sort of the ecosystem of connected products, analytics from those commercial fleets, servicing those commercial vehicles, and the logistical planning around that all depends on hyperscale data. And then making these vehicles and driving safer. Right? You have to understand driving patterns, the quality of your parts and the test data, different indications of what's happening while driving with these vehicles and how the vehicle reacts. And finally, the vehicle companies want to provide more and more of a personalized experience, which takes these factors that we already talked about into account and looks at software application usage and their trends, predictive maintenance for those vehicles. So when you look at kind of the growth strategy of the automobile companies, underpinned by all of that is the reliance on all of this hyperscale data. And we're going to see how we can solve some of those challenges in the upcoming demo. So what are we really talking about with telematics at Hyperscale? Here, this is an example that kind of displays how much data there is. So by 2025, there'll be 116 million connected cars in the US. And each of those cars is predicted to create 25 gigabytes of data into the cloud per hour. So when you do the math on that, that's 219 terabytes each year by 2025. And it works out to roughly 25 billion terabytes for all the cars that are out there, right? So tremendous amount of data. And the telematics data itself is captured on the vehicles and communicate diagnostic data points at set intervals. Typically there's a location element to this and a timestamp. You might have information about battery levels and other IoT data on parts and how the vehicle's performing. And then telematics for fleets of thousands of vehicles at 1 second intervals are going to generate trillions of data points, which these automobile companies have to analyze to solve the challenges that we talked about in the previous slide. So really quickly, what is Ocient? Ocient's a complete hyperscale data analytics solution that starts with the ability to load and stream in data from a variety of different sources and formats, transform that data, and store it in our hyperscale data warehouse, where we rely on NVMe compute, erasure encoding. We have many different secondary indexes for performance at this scale. We also have complex data types like tuples, arrays, and geospatial data. And then we open that data up for analytics through SQL in our SQL engine, where we do interactive performance at Hyperscale, and we support all of the standard SQL statements and functions. We can join data, we have workload management, We can even do things like machine learning and training in the database, which we'll talk about a little bit. And then we have the ability to do ELT within the database and move data around as well. And our transformations during load time, they're scalable and they can get pretty complex with what we support. And with the variety of data that's coming in to solve these problems in the automotive space, some of that data does need to be transformed quite a bit. Ocient runs in our cloud, the Ocient cloud, which is a fully managed solution by Ocient. We can run in the public cloud, and then we have an on-premise solution as well. So customers typically connect through our ODBC, JDBC, and Python drivers, and you can connect through all the typical connections from homegrown applications to BI tools to data exploration tools and so on. And so that's the solution stack, a quick overview of the solution stack from Ocient. Now, how does that factor into solving these automotive challenges as we go forward? Well, the data is coming in from parts data, test data, battery data. We have trip data, which includes geographic data, data about the user, right, and what they're doing, and weather data, right? So we've got a wide variety of data sources that can come in, and we have the ability to transform those and get them into a structure that's optimized to run analytics on, and we can also optimally store those at scale. And then the use cases that we're looking at are map change detection, trade area analysis, battery and parts optimization, delivery fleets analysis, infrastructure optimization. So this is an example of how the Ocient solution stack applies to analyzing hyperscale, automotive, and telematics data. So where does Ocient fit in the ecosystem of data analytics tools? So you notice up here in the top right, we excel when the size of the active data set is in the hundreds of terabytes and beyond range. Right? So Ocient's very focused on providing interactive analytics when you truly need to analyze these hyperscale data sets. So what we mean by active data set is not just that the data is stored, but the data is being actively analyzed in one or many queries. Right? And when you need all of that data to be available, or a very large set of it, that's where Ocient excels when compared to these other tools. Okay, so why is Ocient a great solution for geospatial analytics? Well, we have leading functionality in geospatial when it comes to our data types and functions supported. We've invested a lot of time into building out a complete geospatial offering when it comes to SQL functionality. I think we're up to something around 120 geospatial functions that are all working based on the ANSI SQL geospatial standard. The underlying architecture of Ocient allows us to perform at hyperscale and factor all that geospatial processing into the mix and the analytics, right? So we're piggybacking off of that solution stack that I talked about a few slides ago, and we're aiming towards interactive performance with geospatial data and functionality. And performance at hyperscale with geospatial is a very challenging problem to solve, and it really requires companies who are dedicated to solving that problem to do it well. And then finally, we have a full SQL data warehouse with ML functionality that you can use with all the geospatial processing. So usually, these data sets aren't only location data, they also include other columns, other data types, other things you want to join on, timestamps, right? So you can leverage the full power of the data warehouse and machine learning with your geospatial all in one place. Okay, so now we're going to switch over and talk about the demo itself. So we built this demo based on publicly available taxi data that the city of Chicago publishes. Right? So they've published 150 million taxi trips from 2013 to 2022. And we took those 150 million trips, which they give you a start and an end point, and we generated 250 billion trip points along those trips, right? And we did that at second by second intervals. So if we were given a start and end point of two locations, we generated the trips, the exact path of the trips at second intervals along that. And ultimately, we have 250 billion points stored for this demo. And the things that we store at each point, we store longitude, latitude, we have battery charge information, we have charge percentage, we've got a time, we've got the geospatial point value of this location. Additionally, we created charging station locations, right? So these are charging stations throughout Chicago, and you'll see how we leverage those. And we also generate charging events for each of the stations, right? So a charging event is when a car pulls up and charges, and then charges to a certain percentage and then takes off, right? And then finally, we have data about the type of vehicle. So for each of the vehicles going along these paths, what kind of vehicle is it, and what are some other properties about that vehicle? So that's a quick overview of the data itself. But sometimes it's hard to understand really in 250 billion telematic data points. How large is that really? Well, an example: GM sold over 500,000 electric vehicles in 2021, and if we were capturing telematic data at 1 second intervals, each of those vehicles might generate around 250,000 data points per month at 10% usage, so if they were being used 10% of the time, and that would mean 250 data points in less than 2 months for their fleet of electric vehicles. And another way to look at how large this data set is 250 billion telematic data points represents around 7,900 years of driving time at 1 second granularity. And so a tremendous amount of data here that we're using in the demo. And what we're going to do in the demo is first we're going to understand the utilization of the current charging stations. Then we're going to identify areas for new charging stations. And then finally we're going to analyze battery performance for vehicles in Chicago. So let's take a look at the first query we're going to show. So in this one, we're not using any of the real performance optimization techniques or tools that we can use in Ocient. We're just running this relying on the raw power of the architecture itself. So we're not doing time partitioning, clustering, secondary indexes. What we're doing in this query specifically is we're trying to identify a set of charging stations that the company might want to go out and look into further. Right? So first we look at what are the distances between each charging station to every other charging station. So can we find these charging stations that are either very close or set off in some distant location? What are the least used charging stations by average event duration? Right? So people show up and have a charging event, they charge their car. What are the least used by how long each car stays there? And then what are the least used charging stations from a number of events? So which charging stations are having the least charging events and cars coming up and using them? And then finally, what are the least visited charging stations by unique vehicles? Right? So where are the least unique vehicles using charging stations? And then what we're going to do is we're going to union all of these together and sort the list. So this will give us a view of our charging stations of interest, and we'll see how quickly this runs. So we're running this demo in Metabase, which is a BI tool, and when I click on charging stations of interest, you can see it's doing science, and now it just ran that query against all of our charging station locations and events, and did essentially the 4 queries in one, union them together all in a matter of seconds. So now someone could go off and take this and go out and look at, okay, there are 4 of these properties were met at the Taylor Street Library and Apartments. Maybe we should go look in, see if there's something going on with that charging station, or any other reason we'd want to look into it to make sure it's working effectively. Okay. So the next thing we want to look at is understanding where to place a new charging station. So in this one, we are going to use a number of the different performance enhancements that you can get through Ocient, in addition to leveraging the Casa architecture. And so we're going to use time partitioning. In this query, we're going against the 250 plus billion record table of trip details. We're going to use some secondary indexing to isolate the relevant battery charge. We're going to be doing distance calculations. We're going to be clustering geographic data to determine where the clusters of points are that might represent a new charging station. And then we're going to create a couple geospatial objects in this single query. So all of this is happening in one query. And let's take a look at what this query is doing. So the first thing we're going to do is we're going to select the low battery levels from the hundreds of billions of data points captured along these trips. So at each one of the data points, we're looking at where is the battery level below a certain point. And then we're going to use some geospatial functions to find the points of those low battery areas that are furthest from available charging stations. And then finally, we're going to take all of those points and we're going to call a cluster DB scan, which is going to look for where are the clusters of these points where cars are running out of battery and they're far from a charging station. And then we are going to look for the centroid location, so the center of that cluster, and we are going to finally draw a circle around it. Right? So create another geospatial object here. And let's go ahead and run this query and show how fast this runs. So if I go into charging station deserts full year, you can see this query is running now. It's doing the time filtering, it's doing the geospatial functions, it's creating the new polygon, and it did that all in a matter of seconds against that 250 billion record table. So really impressive. And what it would look like if we were to show those locations on a map is this. Right? So we would see, okay, this looks like a potential area of a charging station desert. We might want a station here, 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 and here. And so all of that work was just performed in Ocient in, I don't know, 5 or 6 seconds. Okay, the next thing we're going to do is we're going to look at the analysis of battery performance. Right? So battery performance is a very important factor when it comes to the automobiles companies to differentiate themselves and get people to adopt to electric vehicles. So the first couple we're going to look at are pretty straightforward. In this one, we're examining the battery range for individual car models over time. And so for each model of a car within a brand, we're going to show the average battery range and how it decreases over the number of years of use. Let's go back in and we're going to show the model battery degradation over time. And you can see for Chevrolet, you can see the Bolt EUV and the Bolt EV that over time by month throughout these 5 years, the total capacity of the batteries are going down by brand. And if we put in Ford, for example, this query now, when I put that in, it's rerunning. It's actually rerunning. We didn't cache the data, and you can see the battery degradation for different Mustangs over time throughout the same time period. Okay. Now what we're going to look at is we're going to look at the battery degradation by long-term use for all of the vehicles. So in this one, we'll be looking at the total set of vehicles and getting the average percentage of remaining battery capacity when they're out in the field for a number of years, right? So that they have a number of years in service, and then we see based on those years of service and based on all of the 250 billion trip points and all of their batteries and the charging, their battery levels and the charging events, how is that capacity changing over time for the entire fleet? So let's go take a look at that one. And you'll see in this one that, you know, as the cars of the fleet are in the years of service, as their years of service increase, their total capacity for charging decreases over time. And so for this example, these vehicles that have been in service for 5 years, they went from, you know, 98% to having 94.37% of their total battery capacity. Okay, pretty cool. So the next thing we're going to do is we're going to look at this data using machine learning and see what predictions we can make related to battery discharge and temperature. Okay? So Ocient has several models for machine learning. And in this example, we're going to model the relationship between battery discharge per mile and the average daily temperature. We're going to show examples with both simple linear regression and polynomial regression, and we train these models over 2 million data points. So let's look at how we do this in Ocient. So machine learning against very large sets of data like the data in this demo is very easy to use in Ocient, and you can keep all the data in one place and do this very quickly. So the first thing we do is we create a SQL statement to generate the features and identify the training set for the data. And then we take that SQL statement, we put it into a create model DDL statement. So this is similar to any other DDL statement like a create table, but we're creating a model where we're putting the training data set in, which will be the result of the SQL statement identified in step 1. And then once the model's trained, we can call that model as a function in another SQL statement. Right? So we built our temp mod model, and here you can see we're selecting temp mod against data in the temperatures table. So let's go in and we'll look at what the machine learning models tell us on temperature versus battery discharge. So first we're going to look at a linear regression model against this data. So thinking about that last slide I showed, we've already done the identification of the training set and generated that SQL. We've trained the model, and now we're calling it against the temperature table. So what we're looking at is, here are the actual discharges at different temperatures here on the x-axis. So you can see the temperatures in degrees Fahrenheit, and then you can see the prediction of the linear regression model. And you can see the linear regression model is not really a good fit for this. And it's not a linear, the relationship between temperature and discharge isn't a linear relationship, because, you know, as the temperature is very low, you're heating the car and the battery is performing in different ways, so you're discharging more energy at the lower temperatures, and then things kind of level off here between 30 and 70 degrees, and then when you get above 75 degrees, the discharge of the battery goes up again because you're running the AC and you're using more power in the car. Okay, so now we're going to show a polynomial regression on the same data and see if we can predict the battery discharge any better with a polynomial model. Right? So when I click on the polynomial regression, again, this is running the polynomial regression now instead of the simple linear regression against the same data set. And we'll see if this model's a better fit. And what we're going to see when this comes back, and this is again calling that polynomial regression against the same data set, is that now we actually do have a pretty good fit. So our predicted battery discharge versus the actual discharge here is quite good. So we could use this to potentially predict discharge at a given temperature. Well, that was it for the demo. That quick summary. Ocient is ideally suited to manage hyperscale telemetrics data both efficiently and effectively. We put a lot of work into our geospatial functions and geospatial data types and machine learning, and we do all of this at the Ocient scale and interactive performance level. Our indexing, which runs on a variety of different data types, it helps enable access to the trillions of data points in seconds, whether or not it's on a geospatial column. The ability to define secondary indexing is hugely important at this scale, right, to narrow down the data set. Like I mentioned, we have a wide variety of geospatial function support, in addition to a wide variety of transformation capabilities that can be used to get the data into Ocient, and even further transform it through things like create table as select to get into a final design or a final schema for running your analytics. And then in the last couple examples of the demo, we took a look at how easy it is to do machine learning against data at this scale in Ocient, all without moving data around and using SQL, which you're familiar with from running all of your other analytics. Thanks again for your time today. You can always go to ocient.com for more information or reach out to us for a demo. We look forward to helping you solve your challenges with geospatial data at Hyperscale.